Hello, September 7th. All right, let's do this. Good. Think we can go to bed early today. Convert integer into sum of two non-zero integers. No zero integer is a positive integer that does not contain any zero in its decimal representation. Given an integer n, return a list of two integers where both are no zero integers and the sum equal to an n. The test case is generated so that there is at least one valid solution. If there are many valid, you can return any one of them. Oh, any one of them. I thought you need to list all of them. I was like, okay, if you need to list all of them, that doesn't feel very simple. We are just going to... Hold on. I just... yeah. So what, we just start from 1? I mean, I'm also 10 to the 4th, so we just start from 1, and then you go through everyone, and then all you need to do is to check, right? That's what you need to do. You need to check if it contains any 0. How do we check? We can check by turning it into a string, and then check the string. That's the thing. If it ends at 1, then obviously we cannot do it that way. So we have to use maybe 2. But if we, for example, I think 100 is not a good example. 101 is also not a good example. I think maybe this. So this has to be a very different number, right? Because 1, 2, 3, 4, like all the way to 20 doesn't work. So it has to be 30, maybe 32, 22. Okay, 22 works. 22 works. And if we have multiple zeros, you know, we have, let's say, 8. Okay, 1, 2, 3, 4. Oh, okay, I don't think I can do it this way. Oh well, I mean, it's all right. I think we'll just go one by one. Just trying to think if there are any fancier way of doing this. I think the easiest would be just, you know, we'll do it one by one. And nothing fancy. Oh shoot. Nothing fancy. We'll just do it one by one. Brute force, since n is no more than 10 to the 4th. So we do need to check, right? So to check, I wonder if the starting number can be, you play some trick on the starting number so you can immediately skip. Like you don't do 100, you go directly to 111. Yeah, the starting point is, I'm too lazy. Too lazy. I think I'll just check. Maybe I can do a lambda. I can say auto check 0 integer. Okay. So this one will be, I think we don't need to take anything. So we're passing a number, and then we will return whether it's true or false. All right, come in. pain was, everything's hurting.
Right, don't do it. I don't know what you mean.
I only did 3 sets on bench, but I also go for like I did 8 sets and it's already past 8. Yeah, I did 3 sets and it's already past 9 p.m. Like, nah, I don't know. Be on bench. No, just do regular training. I mean, it's tough, but I think I actually think I can do it honestly. But it's already past 9 p.m. and I got to work. And then because it hurt, like I can't even do arch. When I arch, my back hurts, my glute hurts, everything hurts. Well, then it's not up. I don't think I can do leg up on the street though. But yeah, it's alright. I think it's some random from that. Right. Wow, this is glorious lighting. Glorious lighting. It's women. Squat tomorrow. All right, I'm back. All right, let's do this. So we need this to check if there's any 0 in it. So what I want to do is turn it into a string and then see if there's a 0. All right, I forgot how to do toString. Is that toString? Integer toString. Is it called toString? Yes. You call toString. Okay, so what we're gonna do is string. Hold on, I need to do this. So string num str to string num. Okay, and then we'll return. Actually, don't know. Can I say string contains char? I think I just call contains. Yep, I think it's just called contains. So we say return num str dot contains. Why it doesn't show me? I don't know. Huh. C++ 23 and later. I might not have C++ 23. Actually, I don't know what version I'm using. So maybe we do .find. Okay, I think I probably have .find. Yep, I have .find. 0 is not equal to std. I forgot. So no op. Std string no op. If it doesn't, then we have contain. Yeah, string no op. Right, that's it. Yeah. Okay. So this is check. That's is 0 integer. So if this true means it is no. It should be equal to. Wait, 0 integers contains, right? No. This is, so if it's true, that means it's a 0 integer. If it's false, which means it's equal to no op, then it's not a 0 integer. Okay. So with that, we can say for int I equal to 1, I smaller than n, I plus, if is 0 integer, I, actually, if this is not, and this is not, is 0 integer n minus I, then we'll return I n minus I. This should return this. Okay. All right. I think that shall do. That shall do. Okay. Maybe there is an easier way. Most likely there is an easier way. Let's see. Let's see the editorial. Oh, look at that. Huh. I didn't think about that. That's actually a better way. I mean, I made 2 function calls. Yeah, it's the same. Okay, yeah, that's all right. I don't know. I said I want to look into this problem, but this one doesn't have an editorial, so I guess we just don't deal with this one anymore. I think this is the one I do for fun, right? How did I do it? Oh. Actually, I don't know. Seems complicated. Oh, there's some hints. I can read the hints. I never really do the hints. Okay, let me understand the problem again. We have value and a limit. All elements are inactive. You may activate them in any order. To activate an inactive element at I, the number of currently active elements must be strictly less than this. When you activate the element at index I, it adds value to total activation value. After each activation, if the number of currently active elements become X, then all elements J with the limit is smaller than X becomes permanently inactive, even if they are already active. The maximum totals, okay. So what I say is I'll make the limit the key and all the values to the limit, and append all the values to the limit and sort it in descent. We go from the smallest limit, because if we have a small limit, because a small limit, those one will get deactivated earlier, right? If you have a large limit, then you can wait until later, because you have a small limit, and you get, if you don't do it, they activate something else, and the small limit becomes smaller than the current active, and they all become deactivated. So you don't want to do that. So we start from the small, and then for each limit we add the limit. We can add a limit number of values. Yes, if we have 2 limits, we can add basically 2 values. So if we add from large to small, we get the max values available for the given limit. That is correct. Once the limit is hit, we have to deactivate all the elements added for the current limit. Then we move on to the next limit. Okay, so this is what I do. I have a map. I have the limit, push it back. I do the sort from large to small. This is the number of active. This is the result. And this is, what's this? It's activated. Limit, number of activated. So this, because every time the limit got hit, I have to deactivate all these things. This is the index on activated array. Activated array. Okay. Oh, this is an array. This is an array. So I always point. So once I deactivate, I move on to the next one. Okay. So this is the map. I go here, limit values. What I do is I is smaller than value size. Yes, and the current active is smaller than limit. I'll add the value. Increment active, increment added. This is the number that gets added for now. And then while J is smaller than activated dot size, if activated J dot first, which is the number activated, the limit. If the limit is smaller or equal to, then the active needs to be deactivated and move forward, right? And then once we're done, we move I forward. So every time we add a new one, we'll check if we need to deactivate something else. So once we finish everything, we'll add it to, oh, this actually looks pretty nice. I think this is looks good. Group the limits by their limit as decisions for each limit are independent. For a group of limit equal to j and m items, its contribution is the sum of the top j to m values. That is correct. To extract each group's top value, we use a main heap of capacity j. Push each value, and whenever the heap size exceeds j, we pop the smallest. Extract each group's top values. Oh, okay, so yeah, that's fine. After processing group's heap, sum its elements and add to the overall total. Repeat for the group in any order. Wait a second. This is saying we just need to find the top m for everyone, and then we just add them. You don't have to go through this process. Oh, I think this is correct. I think we're making this more complicated than it needs to be. All right, let's, I think this is, what, 3, 6, 4, 5, yeah. I'm gonna follow the hint. So this solution follows the hint, which essentially says we say that we only need to sum up the top m values for each limit of size m. It makes sense, right? This makes sense because for each limit m, we can add no more than m, actually not m, it's m minus 1. Right? No more than m minus 1 number of values. Or it's m values. No, it's m. Once it reaches, then we'll deactivate. Yeah, it's m. No more than m numbers of values, right? Once m is hit, we deactivate everybody. And the total number of activated values becomes 0 again. Thus, each limit can be processed independently. All right, so what we're gonna do is the same thing. We use a heap. We use a heap a max heap. And then we sum everything in the heap. Okay, so we say td map priority queue of int. Right, so max heap. Actually, no, I think it needs to be a min heap. Right, it needs to be a min heap because we need to keep the top max. Right, the top max in it. Min heap, so if the current value is larger than, we pop the min, we push it in. If it's smaller than the min, so we don't even push it in. So how to define a min heap? I forgot. Yes. We will use a min heap to keep track of the top m values for a given limit. All right, so we say if m limit I dot size is smaller than, now is equal to m now if it's smaller than, then we just add. If it's bigger than and this, then we need to pop and then add. And otherwise we don't do. Okay, so let's say if it's smaller than limit I, then we say m limit I dot insert push value I, else if, so it's equal to, and limit I is larger than m limit, no, not limit I, my bad, it's value I is larger than this dot top, which is the smallest. Then we say m limit I dot pop and then m limit I dot push value I. Otherwise we don't do anything. Okay, so this is done, and then long rest equal to 0 for const auto p of m for int v of p dot second rest plus equal to static cast long v, or I can do long here. Ooh, I cannot do that. Okay, so while p dot second dot empty, well, it's not empty. Rest plus equal to static cast long p dot second dot top p dot second dot pop. What is wrong? P dot second dot pop, because it's const. We can't use const. And no return rest. Alright, let's give this a shot. Yeah, that is the solution. 333. %. All right, that will be it.